If you came to the keynote this morning, you might recall I had an architecture diagram that talked about a Hewlett-Packard-like use case. This is really a talk that kind of drills into what it's like to try to do data processing with microservices as opposed to like using Spark and Flink and stuff like that, the kind of classic tools for data. I will talk a little bit about when you should use those instead of microservices, but it's sort of designed to kind of look at this what-if scenario and why this might be a good idea. The pictures, I usually put in photographs of backpacking trips in my talks, and these happen to be from Glacier National Park in Montana in the US. And of course, this is the sunrise, as you maybe can tell. And this was the day before. All right, let's make sure I have this right. So what we're going to do is talk a little bit about stuff in this report that I mentioned this morning. We just came out with a second edition, and you can get it at this link, lightbend.com, Fast Data Platform. You'll probably get an email from the conference from Lightbend anyway about this report, but it goes into a lot more detail than we have time for today. And so from that report, I sort of created this architecture that's, you know, maybe a representational architecture, something you could riff on for your own needs. And you may recall it looks something like this. In this case, we're just going to focus on the two things that are circled, processing with Akka Streams and Kafka as the data backplane for the whole system. One thing that occurred to me recently, if you look at these two circled things, they're kind of the streaming analogs of like a database in a more batch or a data at rest context, where you have something that's storing data for you and then something that's giving you the ability to analyze it, you know, ask questions of it and so forth. Here, of course, we're talking about a streaming scenario, but we still have storage and then separate compute in this case. All right, let's first talk about Kafka. How many of you have actually used Kafka or plan to use it? Yeah, I kind of figured it's fairly well-trodden territory. I'll just briefly talk about some of the highlights of Kafka for those of you that aren't that familiar with it. And that'll be this part. So you deploy Kafka as like a small cluster of brokers. Those are like the master processes, usually in an odd number for failover and resiliency, the usual story. You'll notice zookeepers in this diagram. That's for federating masters and that kind of stuff with Kafka. Your data is organized into topics, much like message queues, where you organize data by interest in queues, and so you don't have to absorb everything. When you're a reader, you can just read the topics you care about, like, you know, credit card transactions, clicks on the website, et cetera. And you can partition them for horizontal scalability. Now, what Kafka guarantees is that ordering is preserved by partition, but not by topic. So in topic A here, I don't get global ordering over the topic, but I do get ordering per partition. And if you partition by hashing keys, that's usually all you really care about. Like, I want to make sure that every customer transaction for a given customer is maintained in the right order, that sort of thing. But now I can have parallel processing over these partitions, so this is one way I scale. And I can replicate these things across the cluster for better resiliency and all that kind of stuff. I can have as many producers as I want writing to the end of this topic, and then as many consumers as I want. But here's an interesting and important difference between Kafka and traditional message queues. The consumers can start at whatever offset they want, and in fact, they don't have to read in any order. They can just hop around if they want. They could do like a Turing machine or something if they really wanted to. That also means that in a queue, normally, as soon as you read it, you pop the item off the queue so that only one consumer would actually see any one message. But let's suppose these three consumers were actually doing entirely different things. Like, one was training a machine learning model, one was updating a database, one was feeding a dashboard or something. All three want to see the whole stream of events. So you really want them all to be able to see everything. And this queue model of popping things off the queue automatically would just not work in that case. So what Kafka does instead is it manages the life cycle of the contents of the topics. And the consumers can read any way they want. Usually the life cycle is like, you know, 7 days or maybe size or something like that. It could be bigger or smaller. But that is what makes Kafka different than a queue system, and really the term is it's a log system. in a sort of a general sense of what a log is. Architecturally, Kafka is very valuable for simplifying your architecture. So I drew this ugly looking, totally bipartite graph, which if you were the architect and trying to comprehend your system, it'd be kind of difficult maybe to follow what's going on. Obviously this is a small example, but once you scale it up. But maybe worse than just comprehending what's happening with all these point-to-point connections is, what happens if one of these things dies on the right-hand side? Then you've got potential data loss because there's nowhere for the data to go in the direct connection. And probably you can't stand up a replacement fast enough to keep the socket healthy or whatever. Well, we learned in computer science that you always solve any problem with another level of indirection. So we'll stick Kafka in the middle and basically solve our problem. Not only do we get architectural simplicity by, the picture is simpler, so it must be simpler, right? But we also get this resiliency. A service goes down, data can still be reliably captured in Kafka and then read when it comes back up. We can have really nice decoupling of producers and consumers of data. The folks on the right don't have any idea where the data came from on the left, and we can add and remove producers and consumers. So it's a really architecturally good model to follow. And of course, you could do this with message queues too. That's not a new idea to have this kind of integration point. So we simplify our dependencies, we have resilience against data loss, arbitrary number of producers and consumers. And also, I didn't get to this yet, but if all you know how to do is talk to Kafka, like read and write topics, that's a very simple way to communicate. I only have to learn one API effectively. So it's a nice way to integrate things without having to learn every special case. Okay, so that was the storage piece, right? So now let's talk about the streaming engines. And let's start with talking about Spark and Flink and when you really should use those instead of these microservice libraries. Well, these tools are really great for doing some very important things, which are you throw a big wad of data at them and they automatically figure out how to partition the data across the cluster to run, to schedule tasks that are actually going to process the data for the job you've submitted. And they do all this in the background. They manage these tasks in case they fail. Do a lot of coordination that you don't have to do it yourself. So it's one of those great tools for that purpose. Now the reason Beam is in the diagram, and I go into this a lot in the report, is Apache Beam is Google's data flow, which they donated part of it, and I won't get into a lot of details, but they donated part of it to the Apache Foundation. And the Beam project is very influential in terms of thinking through all of the issues you have to deal with if you're trying to do very precise calculations in a streaming context. Like, what do I do if data arrives later than when I wanted to do a calculation and so forth? So it's been very influential, especially in Spark and Flink. In fact, the way it's organized, you can even define data flows in Beam and run them in Spark and Flink, for example. And the ideas have also influenced Akka Streams and Kafka Streams to one degree or another. So that's why Beam is here. So going back to Spark and Flink though, so you submit a job, you've written a program in Spark, or you've just brought up a shell and you're running queries or interactive commands or whatever, and that work is submitted to a cluster manager, and the details vary depending on whether it's Kubernetes or Mesos or Yarn, whatever. And then it's delegated to executors that are running on each of the nodes in your cluster to figure out what tasks to run and to manage them and so forth. A lot of stuff that's going on. But wait, there's more. So I mentioned this partitioning thing. Well, here's sort of a sketch of what's going on. Suppose that my data set is already partitioned on HDFS in like 4 basically file system blocks. It'll automatically spin up 4 parallel JVMs. I may have a series of steps I've said to do, but it can figure out, well, I can actually shotgun all of these together at the beginning, the first 3 here, because they don't require me to move data between partitions. But if I do something like a join, which I'm showing here, then now I have to shuffle keys and records across the cluster, so that's going to trigger another set of JVM processes and on and on and on. Again, all of this is going on behind the scenes. It's useful to know what's going on if you're trying to debug a Spark job, but in a lot of ways it's just sort of black box magic. Now, if you're using a library instead, and that's kind of a key thing to keep in mind about what Akka Streams and Kafka Streams are, they are libraries that you embed in your services. Well, you have to do a lot of that yourself if you need that kind of scalability, but you get other benefits if you don't have to have that kind of scalability. So the idea here is, what if we are really good at editing microservices? We have a CI/CD pipeline. We know how to deploy them. We know how to debug them. We know how to monitor them. Wouldn't it be great if we could just keep doing microservices for all our data processing? That's partly the motivation for why we're talking about this. All right, well, we know we're supposed to microservice all the things because we like longer latencies and we like losing the reliability of function calls. Anyway. I came up with this diagram as a way of really setting the stage for how to think about Kafka Streams versus Akka Streams. What's their mental model, if you will, and which one should I pick over the other? So one way to think about the data that's flowing through your system is on the left-hand spectrum, it could just be events, things like authorized credit card, add item to shopping cart, the usual kind of stuff where there's some specific handling that's going to happen. There might be a state transition that's going to happen, complex event processing, all these buzzwords. But maybe on the right-hand side, I might be just dealing with records of data, where in a sense, in sort of this like data warehousing sense, they're anonymous. I don't need to handle them individually necessarily, but maybe I want to do things like filter all of them, transform all of them, group them together, join them with historical data, that sort of thing. And of course, there's no hard line between these. There are times when I might take my events and do data warehousing kind of analytics on them and vice versa. So, but it's actually useful to think about this diagram when you think about Akka Streams versus Kafka Streams. So again, each item on the left-hand side is kind of an identity. We may have to process them uniquely, or at least logically that's how we do it. We might still do it in batch in some way, but logically we think of each one as being unique and special. And often we're manipulating state machines, changing sessions in some way, and so forth. Whereas on the left, fancy, huh? Like that? More anonymous. We can maybe process them in mass. We get the benefits of batch or mini batch processing for economies of scale. Sort of the sort of thing you do with SQL. Okay. Well, Akka came out of the left-hand side of this picture. Akka has always been about microservices, complex state, persisting state, like with Akka persistence, the kind of stuff that many of you have probably been building for a while, or maybe you're learning how to build. And that kind of thinking about that sort of problem is what permeates the design of the features that are exposed in Akka Streams. Whereas in contrast, when they set out to write Kafka Streams, they were really thinking about the problems that the people on the right-hand side, the sort of data engineers were thinking about. Like, they'll want to do joins, they'll want to do group bys, they'll do filtering and transforming. And in fact, Kafka Streams even has a SQL engine. You can actually write SQL queries against your stream to get data right out of the running stream, whereas that's not something supported in Akka Streams. Now, that's not to say that these tools can't be used on the other side of the spectrum. It just means that you might find one versus the other if you're trying to decide which one to use. This kind of challenge, like what am I actually going to do with it, may affect your decision. And as we'll see, you can actually kind of use them together too in some ways. Okay, so it's the last talk of the day. Everyone's tired, so what do? You show code, and that's what we're going to do next. Let's talk about Kafka Streams a little bit. Now, I mentioned earlier that Beam has been very influential in kind of defining the semantics of streaming, and this is sort of peeling that onion just a little bit more. So imagine for the sake of argument that I wanted to do calculations every minute, like I want to know how many items I sold in my store per SKU per minute, or something like that. Normally it'd be more like days or whatever, but bear with me, because the diagram says minutes, and I'm not about to change it now. But here's the problem. I've got servers that are actually triggering events, like shopping cart processed, credit card authorized, but networks are not infinitely fast. So the data, even in a good network, the data for those events is going to arrive later on my processing system. So when that minute boundary is hit, I will almost never have all the data for the previous minute. There's a difference that becomes very important between event time, which is kind of the business logic time you care about. When did I actually authorize that credit card? When did I actually make that stock trade? Versus the processing time when I did something with that data. Like early versions of Spark, the old Spark Streaming API only understood processing time. It had no concept of event time, and that's something the new version of Spark Streaming does support. But it can actually get a lot worse than this. So suppose there's a network partition between server 2 and the processing or the analysis server. You know, it might be hours before I get the data. So then I have this problem of, well, how long am I willing to wait to get that data? Do I send off a preliminary result because people downstream need an answer, let's say in the next minute, and then have some mechanism to send a correction later, like, you know, like they do with double entry bookkeeping, like accountants do. If they make a mistake, they never erase anything, they just add a correction later on in their ledger. So there's a whole lot of these kind of semantics that the Beam folks have thought about you know, when they're trying to push the envelope about what's possible with streaming analysis. When you want to really be able to do something completely in a streaming context that's actually accurate enough to be used for an accounting system, let's say. Now, this inevitably requires us to have a built-in notion of windows, because obviously if I'm building a streaming system, you know, suppose that Amazon was going to calculate the calculation we just described, but they decided, you know what, we'll just wait until we have all of the data that we're ever going to get. You know, they would probably wait for decades, maybe, or however long. So we actually need to think about windows, like, okay, in this case, a minute window makes sense, but there may be windows of time in which we do these kind of analytics, these aggregations, these joins, whatever. I go into this a little bit more in that report, and actually I really point you to much better information about this. It's written by the people from the Beam team, the Dream Beam team. Okay, some features of Kafka Streams, and then we'll get to an example. They do have this exactly once feature. You can really concoct scenarios where that doesn't always work, but basically it's a transaction across the Kafka topics feature so that you can, most of the time, not have to worry about dealing with you know, at least once semantics or at most once and so forth. But it really is effectively once if you want to be very pedantic about it. They have this notion, two abstractions. One is called a K-stream, which is the normal way we think of Kafka as like an event-sourced log. You know, I want to see everything in history. But the dual of that is like a normal database table where maybe I actually only want to see the last record for a given key. Maybe I'm building up an aggregation and my dashboard only cares about what's currently, you know, the transaction rate per minute or something. So they have a K-table abstraction for this, which is really nice. One of the limitations of Kafka Streams is it really is Kafka-centric in the sense that it's only designed to read and write Kafka topics, or also in-memory reads and writes. That means that if you want to talk directly to a database or read directly from a socket or something, then you have to use something else. The way you do load balancing and scaling, sort of the way I described that Spark and Flink do for you automatically, is you basically use topic partitioning as we described, and then you spin up, without getting into a lot of detail, you spin up the number of instances to manage that concurrency. There is a Java API, the original one. Lightbend actually wrote the Scala API, which is actually almost identical to the Java API, just type checks better. If you've tried to use the Java API in Scala, it's kind of an ugly experience. So we just kind of fixed that without trying to change the semantics in any way. And as I mentioned, there's a SQL API. Okay, so the example is actually taken from a tutorial that Boris Lublinsky and I did early this week. I guess it was Sunday? Maybe it was Monday, actually. And the idea is I want to be able to score machine learning model. I want to train machine learning models. Let's say I'm looking for credit card fraud or something. And then I want to serve them in real time in my stream and periodically update the model as you know, it grows stale over time. I want to update it. So what we're going to do is use that Scala API that we donated to the Kafka project. And there's a link here. You can get the slides afterwards. But if you know what queryable state is in Kafka Streams, and I won't take the time to explain it, we also wrote this convenient utility for writing queries against the running state of the stream that you might want to check out. I don't think you can actually see it, but there's actually a bunch of little goats. The little white dots up near the top are a bunch of goats on this cliff. Okay, as I said, this example is adapted from this tutorial, which is on GitHub if you want to dive into it. Okay, code, here we go. So I'm not going to go into a lot of elaborate detail. What I really want you to get the sense of is, how hard is it to do anything in these APIs? Well, what is it like to work with them for sort of basic transformations and so forth? So we'll just quickly walk through it and just kind of get the gist of it. You always start with a stream builder. That's like your entry point. The stream builder S is the Scala API version of a Java class called stream builder in the Kafka Streams Java API. Now we're going to need two input streams. One will be model parameters for when we periodically update our machine learning model, and the other will be the data that we're actually going to score against it. So that's what these are doing. We're going to use that builder we just instantiated to create two streams. We're just going to read and write raw bytes and then parse them in memory. You convert them to our record types. And this the topic things at the end of the line are what you would imagine. They're just variables that are holding, identifying information about these Kafka topics that we won't go into. A couple of classes we won't describe in detail, but just to give you the gist of them, we'll have a few classes that handle the process of updating the models when they come in. That'll be model and model impl, which is a few lines down. Model processor is actually the thing that will take a data record and score with it. And it will encapsulate the score object, which takes the processor. And so I'm setting up the boilerplate here to make this thing work, basically. All right, here's the important bits right here. We're going to have two streams again. We've already created the initial entry points. What we're going to do is map over each record, and map values is a convenience method they stole from Spark, where if I have key value pairs and I'm not going to change the key, it'd be a lot more convenient if I didn't have to deal with the key. Just pass me the value, I'll do a transformation and return a new value. You associate it with the original key, and that's what map values is. Otherwise, it's just like a regular map. So we're going to parse the model bytes. This is the model data stream, model parameter stream. The second line will filter out failure. So this is production code. We're going to ignore errors, okay? I can tell it's late. We're going to see if we successfully parsed this data, these bytes into model parameters. And then the next steps, the map values and process is where we actually instantiate a new model and put it in place. That's the basic idea. And then something very similar for the actual data scoring. We'll first parse the bytes. If that succeeds, if we got a valid record of some kind back, then we're going to turn that into, we return some abstract data record type, whatever that is. Actually, in the example, it happens to be wine parameters for wine tasting purposes. And we'll do some scoring and return a new record that has the original record and some score, like quality or price or something. Oh, and then this one is slightly different. So once we've scored that record, we're going to write it out to a new topic. That's what this to method does. It sends the result out to another topic for downstream consumption. And then you glue it all together with this Kafka Streams object, pass in a configuration thing that tells you where the brokers are located and that kind of stuff. And then you start it running and you add a shutdown hook. So that's basically it. A little bit of boilerplate, not too much. If you've written anything with the Scala and even the more recent Java collections APIs, it ought to look kind of familiar about how you would process, how you would think about the steps you need to go through to process the data for what is actually a fairly simple model from the data point of view. There's a lot of complexity in machine learning, of course, that we're kind of glossing over here. Okay, what's not to love? It's all great, but it is designed for a very limited purpose, which is data processing for Kafka topics. And you're going to need to wrap this in a whole bunch of other stuff for a typical microservice. So you can use Akka, Play, Logem, the regular Lightbench stuff for the rest of this if you want. And it's a perfectly good way to combine these APIs to get the best of both worlds. All right, let's talk about Akka Streams. So here I'm really preaching to the choir, as it were. I think all of you probably know what reactive streams are. I'll just briefly describe it in case you don't. But Akka Streams implements this protocol, and it's really a backpressure mechanism for flow control so that you don't overwhelm a stream. So here's a kind of a classic scenario where I have a couple consumers watching let me step back a second. I want to hook up a couple of consumers to a producer of data. And the classic way we've always done this is to put a buffer in the middle so that they can kind of go up and down in terms of their processing flow and it won't cause problems. But there are problems, right? If I use a unbounded queue in the middle, because I don't really know how far they could get out of sync, inevitably there'll be a situation that sets up sooner or later, again I'm running these things for months maybe, where the consumers cannot keep up anymore. And the producer is filling up this queue and then runs out of memory and crashes everything. So that's bad. So then we said, all right, well, we can solve that problem by using bounded queues where you can only put in so many records into the queue. But we've only just really pushed the problem in a different direction. We haven't done anything to solve that problem of things getting out of sync in terms of their rates. We've just caused a problem where now the guy pushing stuff into the queue has to make a decision what to do when the queue is full, which will happen again when the scenario sets up. And unfortunately, this is code that's probably deep down inside some application. It really doesn't have the global context. It really doesn't know what it should do to handle this scenario where the queue is full. So that's where backpressure comes in. It's basically a communication control loop, if you will, that tells from the consumer pushed back to the producer, it controls the rate of flow. It turns out usually the way it's implemented is if the consumer's keeping up just fine, it's just a push model because it's very efficient. But if it gets backed up, then it flips to a pull model where the consumer pulls data through. And that way you don't fill up the queue and get into any of these scenarios. The other really great feature of this is it composes. So if I have like a graph of these reactive streams, they will all compose. And if the consumer on the far right starts pushing back, and that gets propagated to the beginning, well, hopefully at the beginning of this graph, I may still have this problem of too much data flowing into the system for what it can handle, but hopefully I can at least make a strategic decision about what to do, like write to a file system and come back later. If it's like a dashboard I'm feeding, maybe I just throw the data away, that sort of thing. Basically, I really have a key lesson, and I don't really call it out so much in the slides, is you either need some massive queue like Kafka topics, or you need something with flow control like Akka Streams. If you don't have one or the other, you're probably going to have unreliable code sooner or later. All right, well, Akka Streams is obviously part of the rest of the Akka ecosystem. I mentioned the limitation that Kafka Streams only talks to Kafka. Alpaca is a really nice library for talking to a wide class of stuff, like databases and Kafka and other things. All right, so I found it difficult to actually get the gist of Akka Streams when I first started learning it, so I decided to write the simplest example I could think of, and that's to calculate factorials. And obviously I didn't want to go too far with this, so I'll calculate the first 10. So here's just a basic example, and I cheated. I left off the import statements, but it turns out that tutorial online I mentioned actually has this as a script that you can run with Scala just to see it work. But it goes like this. We start by defining a source. We need one or more. In this case, it'll just be the integers from 1 to 10 will be my source. It'll be a source of integers. I'm going to scan it, and this is really like fold left for those of you that know that method. I'm going to iterate through these integers, and then I'm going to keep an accumulator and just multiply the previous total with the new value, so I'm computing factorials. And then I need to sync it somewhere, one or more places, so I'm going to run this flow with a sync that just prints to the screen, which I'm showing to the right is what the output would look like. So we have a source, one or more, a flow, and a sync, one or more of those, and those constitute a graph. And that's sort of the essence, really, of Akka Streams. It's sort of defining graphs and processing. Interestingly enough, you can actually have loops. Most systems only support directed acyclic graphs, but you could have like control feedback loops. Or you could crash everything by feeding all the data back in an infinite circle. It's up to you, whatever you like to do. All right, so let's look at the same example, this time implemented with Akka Streams, and I sort of tweaked it a little bit. Now, I really didn't talk about the other logic, the stuff to the right, but here I'm kind of showing that you have a little bit more flexibility about how you lay things out. You don't necessarily have to write everything back to Kafka and read it from Kafka, because there's overhead with that. Maybe you actually just want to do a direct actor message or a composed reactive stream between the model serving part where you do the scoring and whatever is going to be downstream. I mean, you have a little bit more flexibility here. All right, so this is what it looks like. It's conceptually very similar, but obviously the details are different. If you've written any actor code, you know that the first thing you always do is instantiate an actor system. That's your entry point. If you don't know Scala, the implicits, you can kind of ignore that keyword. They're just sort of conveniences, really. One of the interesting things about Akka Streams is it actually does try to separate the notion of defining a stream from how it's materialized. So in principle, you could materialize it with another runtime. Right now, the only one that exists that I know of is using actors, and that's what the second thing does. It's a materializer for that. And then execution context is basically our thread pool that we have control over if we want. We'll use some of the same classes we saw before, but didn't really describe in detail. Something to handle scoring and handle models. An object that does the actual scoring. And then, this is different, we can actually, I mentioned we were building graphs, right? Well, we can actually define nodes in the graph as like reusable libraries, and they're called stages. So we're actually going to take that approach. We'll actually build like a library stage that an application developer could use, for example. And that looks something like this. Obviously, it implements some abstraction, which is graph stage with materialized value. You don't really need to worry about that too much for our purposes. But we can have as many inputs and outputs, are called inlets and outlets. In this case, we need inlets for the data and also for the model parameters, and then the output will be scored records. And then you define a handler that will be called every time there's a new record to process. And the logic here is, actually logic I didn't show before for Kafka Streams, but every time we get a message, we'll go ahead and pass it to our scored, our score object that will then return a new scored record, and then we'll just push that on the output stream. So it's conceptually not difficult. There's a little bit of boilerplate here. So we'll use that, and we'll see that used again in a minute. Now, once again, we need to define two streams. The first one will be some source of data that will be our records. This will be the actual raw data. I mentioned this idea that Kafka Streams has exactly once. Well, the Akka team is very, very careful about terminology like that. So they don't actually give you exactly once, per se. They would rather you be more cautious about these things. So we'll just use it at most once. We'll allow data loss in this case. So we're going to, consumer is also a wrapper around the Kafka consumer API. So we're going to instantiate a consumer with some settings like where are the brokers and all that stuff. Topics we want to subscribe to. In this case, it's the raw data that we talked about. And then when that comes in, we'll do a map over each of those inputs. We'll parse the bytes into a record, hopefully. And then this collect case success stuff is just an idiomatic way in Akka Streams to keep the successfully parsed data. And as we always do in production, ignore the errors. Okay? I hope you know I'm joking about that, of course. The model stream, this again is handling new model parameters, very similar. Just for the sake of time, I won't even talk about it. I'll just remind you that there were a couple of steps we did. We made sure we could parse the parameters, and then we had a few steps where we create a new implementation of the model and give it to the model processor. That's that model processor set model is where we actually instantiate and apply the new model. Now this one, though, I will say at the end, you notice model stream to sync ignore. We don't ever actually need to output anything for the model parameters. We're just going to ingest them, build a new model, ignore errors, again, and then there's nothing to write out. So sync ignore is a way of just saying, I don't need any outputs from this code. So finally, we glue it together. This data stream, again, that's the raw data. We're going to pass it through that model scoring object that popped up a minute ago. The keep right is just an idiomatic thing for Akka Streams, but the output of that will map over it, and we should get a new result of a scored object. And then we're going to write that. Now we do need to write that out to a new Kafka topic. That will be this producer plain sync for some settings. All right, so the logic is very similar. There's obviously API differences. Personally, I think if you already use Akka and you really like the greater flexibility that Akka Streams gives you for really tight control over stream construction, it's probably the best choice. I think there's a little bit more boilerplate with Akka Streams versus Kafka Streams. If you don't know Akka, don't use it, and just want to do data processing kind of things, you're probably better off just starting with Kafka Streams, just as a sort of general hand-wavy way of saying which I think you might want to pick. Okay, let's see, how are we doing for time? Not too bad. I'll wrap up with just a few other concerns. One of them is, when should you not go through Kafka? There is some overhead. There's higher latency. You're actually writing stuff to disk. You're going from one process to another. All of that incurs latency. Actually, it's not on here, but you're also serializing to bytes and then deserializing. You're getting a lot of benefits, as we talked about earlier, but sometimes that's overhead you don't want. So a nice thing about using like reactive streams is you can keep it all in process, no serialization of objects to bytes and all that kind of stuff. But you're also getting tighter coupling between modules that way. Again, use backpressure. If you're not using Kafka, it's really, really valuable to have reactive stream backpressure. And try, just think strategically about which is the better way to organize these things. Okay, so once again, you can get the updated version of this report at lightbend.com, Fast Data Platform. You can hear about the Fast Data Platform that my team developed. Here's the shameless plug. So we basically took a lot of these tools, created a curated, well-tested distribution of them, wrapped some monitoring and management tools. We just announced support for Kubernetes as the runtime environment. We've supported DCOS as the runtime environment. Bring your own storage. Kafka is the data backplane. Fun times ahead if you go with this platform. So I'm told. And that's it. Any questions? Thank you.